Okay. So I'm trying to see how to show the slides, but also show my notes. Does anybody know how to do this on Keynote? Um, is it maybe reverse slideshow?
Oh, your notes on Google Slide?
Yeah. Yeah.
Not exactly sure.
Do you guys see my slides and the notes, or
Yeah, we see. Yeah, we see. Yes.
you guys see the notes?
Yes. Yep.
Okay. All right. Oh well, it's probably fine. All right. All right. Can you guys see my screen?
Yep.
Do you guys only see the slides, or do you see like other things?
See the full screen. You see. No,
Do you see my Slack?
Yeah. No, we don't see your screen. Put it in full screen and.
Okay. Okay, do you guys see my slides?
We see the slide, but we also see everything else.
Yeah.
Oh, really?
We're at the editing window right now.
Oh, that's so weird. That is so weird. Okay, I'm not actually displaying that. Okay, let me stop sharing. Let me start my slideshow. And then let me try sharing again. Sorry, guys. Okay. Okay, now you guys only see the slides, right?
Yes.
Okay. Okay, guys. Well, I'll just go ahead and get started. So right now I'm presenting the BrainLM, a foundational model for brain activity recordings. And so this model works off of self-supervised learning. So in conventional supervised learning methods, these methods depend significantly on the quantity of labeled training data. So as we know in our lab, people like Tu and other people have to manually label data, which can take a really long time. And oftentimes we need people with domain expertise to be able to label data, especially like neurological data or other medical image data. So that's why self-supervised learning techniques, like what I'm going to explain in this paper, are particularly useful. So self-supervised learning basically eliminates the needs for these kinds of annotations and labeled data, which allows a model to learn with the data itself, providing its supervision. So particularly, this paper is using masked prediction training, which basically allows a model to learn the semantics of data without needing any labels. And it overall improves the understanding of the data set without needing specific annotations, all the time needed to label the data set, domain expertise, and other costs associated with supervised learning techniques. So part of this presentation is based heavily on a YouTube channel called AI Coffee Break, where Miss Coffee Bean explains AI concepts to you. I don't know if you guys have ever heard of this YouTube channel, but it's pretty cool. So make sure to check out her channel. I just wanted to give some credits here because I think she's explaining a lot of these concepts better than I could. So yeah. So I'm just getting into some of the background of the paper. I think the most heavily used concept throughout this work is the autoencoder, which is a artificial neural network that reconstructs the input data while being constrained to encode it to a lower dimensional space. So this space is sometimes called a latent representation. But essentially, what this does is it maps a high dimensional input to a lower dimensional input space. And then you just have another artificial neural network that attempts to reconstruct this input image from a constrained lower dimensional space. And since you can use a neural network with nonlinear activation functions, this kind of mapping and reconstruction is kind of like a nonlinear form of PCA. So it's kind of like PCA, where it's like a way to map to lower dimensional space, but rather than with PCA, this is done in a nonlinear way. So it kind of does a better job at capturing nonlinear relationships between features. So so basically, once the input is mapped down to this lower dimensional space, called a latent representation, the decoder neural network just tries to reconstruct the input image up to its original dimensional space. So how does this work? How is this kind of enforced? So it's all you have to do is just take the input, map it down to the lower dimensional space, train a neural network to reconstruct, and then just take the L2 loss between the input image and the reconstructed image. And so that's the objective function that you use to train an autoencoder. So this is kind of an example of what that might look like. The input here is some kind of a medical image that was taken maybe of some kind of an anatomical body part. And then so it's just mapped down to a lower dimensional space. So the output is a reconstructed version of this input. So you can see there's a little bit of loss here, but it's overall pretty good. So in this method, we don't need any labels, obviously. It's just a simple L2 loss between the input and output. So something that's used in images is something called a masked autoencoder. And so how this essentially works is we have an image here that's taken as input. So you can see on the far left is an image of this hot air balloon. And so this image consists of a number of pixels. We don't necessarily know the dimensions of this image as input. But the job of the masked autoencoder is first to segment this image into sections. So these sections are called patches. So these patches are normally like constrained to some dimension. So I think typically it's like 16 by 16. And next, these patches are just kind of aligned and assigned these positional embeddings, which are telling the model where in the original image these patches would correspond to. And after this patching and positional embedding, these images are transformed into some kind of a vector. So how this works is it's some kind of a linear embedding. So you might use something, you might be familiar with something like Word2Vec, which is where you can take a word and actually encode it to a lower dimensional vector representation. And the elements of this vector are just some numerical values that translate to a meaning in this space. And then for the masking part, only a subset of the original image patches are taken and provided as input to an encoder. So this method is naturally sparse. There's no reason to just corrupt these as some kind of a noise. All you need to do is just take only a subset of the original image patches, and the amount that you take is corresponding to something called, I think, the mask ratio. And so you can just kind of play with how many image patches that you want to mask and how many you want to keep. So these image patches, which are encoded to some kind of a vector representation, are passed along with their positional encoding to this encoder. And the encoder is a transformer encoder. So this performs self-attention and multi-head self-attention. And essentially during the training process, what this does is just extract the semantic meaning of these image patches in relation to the other positions in the image. So in the decoder part, the decoder takes the tokens from the latent space, which were output of the encoder, and it computes the original image patches. So what it does is it just tries to realign all of these original patches into the shape of the original input image. So again, how is it able to know where the original image patches came from? It's from this positional encoding part. So I think naturally transformers are a position invariant model due to like self-attention and multi-head self-attention. So these positional codings are needed and required, and they do, preserve some of the original position of the tokens. But yes, so once these image patches are attempted to be learned using the decoder, they're just put back together according to their positional encoding, and the output image is formed. So then you can just use L2 loss between the input image and the output image to train your model. So when it comes to BrainLM, this model was trained on over 67,000 hours. Over 6,000 hours of fMRI data, and it uses this self-supervised mask prediction training. And overall, it excels when it is fine-tuned. So they also added in this prediction of clinical variables and this zero-shot inference for identifying functional networks. And they also introduced this novel prompting technique that enables BrainLM to simulate brain activity responses. So they essentially do this kind of simulation where they slightly modify the input to the model and they analyze the model's response to this disturbance. So this is an overview of their architecture. So they take in data from two different data sets. They use the UK Biobank data set, and they also use the HCP data set. And specifically, they're using the time series of this data set. And the way that they are getting this time series is using Atlas parcelization. And each parcel has its own time series. So I think in our lab, we're mainly just doing the ICA analysis, which gives a set of regions which were identified using ICA, and each region has its own time series. But with this approach, they are just using an anatomical atlas to extract different regions. So again, each anatomical region has its own time series, its own time course. And these time courses are then patchified, kind of like how the masked autoencoder would operate on images. And I'll explain a little bit more of how that works in future slides. But yeah, so these time series are divided into different patches. And these patches, a portion of these patches are provided to their model as input. And their model operates similar to a transformer architecture, in which it takes in a subset of the original time series and along with its positional encoding, and it attempts to reconstruct the time series that was the portions of the time series that were missing. And as well, they kind of explored the latent space, and they also looked at how the model behaves with different disturbances in the model's input. And they also added in some fine-tuning tasks where they tried to predict future brain activity, as well as predicting these clinical variables. So the clinical variables are different data that was collected during the fMRI study of these individuals in the UK Biobank and HCP data sets. So some of these data points include like different survey questions that were asked to the subjects, some of their demographic information, as well as what disorders they were. having at the time. So a little bit of the motivation for this paper is that in neuroscience and computational neuroscience, we have a goal of understanding cognition from brain activity. So we would like to estimate brain activity, but obviously we have to understand what's happening in a person's brain. So we can take a measurement of what's happening in someone's brain using fMRI or other non-invasive techniques. So fMRI is commonly used, and why this kind of problem is non-trivial when working with fMRI data is because fMRI data is high dimensional, and it also has a spatial dimension as well as a temporal dimension. So when working with these spatio-temporal dynamics, it can make the problem complicated, and it can also present these complex relationships across space and time. So another reason why a model like BrainLM would be useful at this moment in time is because nonlinear interactions are challenging for a lot of models that people have used in the past. Something like a GLM or ICA analysis, even seed-based correlations and other machine learning models that have linear assumptions, I think struggle with understanding these nonlinear interactions in the brain. So in addition to that, another need is to utilize the scale and complexity that we have across these large data sets like the UK Biobank and HCP. So if we have a lot of data, we'd like to utilize all of that, and we need an adaptable framework that can fully utilize and be robust in understanding these relationships. So some of the related work that's been done in this problem is early fMRI analysis was using SVM and neural networks. So these models can sometimes be pretty slow, especially in SVM and high dimensional, the high dimensional problem space. And however, a lot of people have been using autoencoders and other mapping techniques for understanding the spatiotemporal relationships in fMRI data. So again, people are liking autoencoders because of their self-supervised nature. And we have limited data set sizes because, it's expensive to label data. It's also sometimes difficult to even capture data sets of individuals using these imaging techniques. So again, these limitations are just constraining the robustness and transferability of these kinds of approaches. So the data sets that were used for this project are the UK Biobank and the Human Connectome Project. Overall, these combined data sets consisted of over 40,000 subjects. And in terms of the model training, 80% of the UK Biobank, which amounts to about 61,000 fMRI recordings, were used in the training. And then the model was validated on the remaining UK Biobank and HCP dataset. And in terms of how the different regions were extracted, a atlas parcellation technique was used. So the AAL atlas was used to segment the brain into 424 regions, where each region has one time course.
Can I ask a question?
Yes.
What does it mean that each region has one time course?
Yeah, so from what I can tell, like their model divides each fMRI recording into these 424 brain regions. And based on their diagrams, it looks like each region has one time course. So you can see like where it says input data, and you see the image of the brain with these little orange regions. So what I'm guessing that they did, which they didn't explicitly state in the paper, was I think they just took the average activation record for a parcel and used that as the time course. But I'm not 100% sure on how parcellation works. If any of you guys have done it before, maybe you know.
You're right, Joanne, it's
I think
never.
that's, yeah, that's generally how it works.
Yeah.
Just average the activity of all the voxels in that region.
Yeah, so obviously, like Sajad brings up a good point, like each region, once you do the parcellation, has like several voxels. So each voxel has its own time series. But yeah, from what I can tell, they just took the average activation of all those voxels time series. Any other questions? Okay. So their model architecture was based on the transformer architecture, something similar to BERT and the vision transformer. So what I explained in the beginning with these, with the masked autoencoder, that is using the vision transformer architecture. But obviously, the data that's used in this study is the time series data. So it uses time series information rather than images. So it uses multi-headed self-attention in the encoder parts to process the visible patches of the time course. And then the decoder is tasked with reconstructing the encoded patches, both the visible and the masked patches. And the time series is embedded and masked. The parcel time series is segmented and partially masked. So this is kind of how that works in a little bit more detail. So the fMRI recordings are segmented. They're segmented into 200 time step subsequences. So from what I understand, they essentially take 200, they take sequences of 200 adjacent time points from each recording. And then from there, they segment those into 10 segments, each segment containing 20 time steps. So next, these segments are embedded into 512 dimensional space. So that's the dimension of the latent space. Oh, no. Yeah, they're embedded into this 512 dimensional space, and then they're masked at ratios of 20%, 50%, or 75%. So the transformer encoder consists of these 4 layers, 4 heads. And the decoder consists of 2 layers. So it was trained for 100 epochs. The batch size was 512, and the atom optimizer was used. And they utilized this mean squared error for the downstream tasks. So yes, they also had this clinical data as well. So they fine-tuned their model for this clinical variable prediction. And how this worked is they appended this MLP head, and they trained for age, neuroticism, score, PTSD, and anxiety. And they also used normalization and scaling. So for the age, I think they used the Z-score to map this to a, they just Z-scored the age values. And then they used min-max for the neuroticism. And they use log transformation plus min-max for PTSD and the anxiety score as well. So then they used this regression task on the unseen data, where they used the UK Biobank test set compared for performance with baseline models using raw data and pre-trained embeddings. And they applied 40% dropout during the fine-tuning parts. Okay, so this is where they talk about this perturbation simulation that they did. So essentially, from what I can tell, the input to the model was slightly altered using a technique. And then they looked at how the model responded to these different disturbances. So this is something that they're claiming as one of their main contributions as well as being novel. So they're calling it in silico perturbation prompting to explore BrainLM's understanding of brain dynamics. So they define this perturbation function, which I'll kind of explain a little bit more on the next slide, modifying the fMRI sequence to simulate cognitive conditions. So they optimized one of the parameters of this function to minimize the distance between the predicted and the target states. So they just kind of wanted to understand their model sensitivity to these kind of task-driven changes in the visual cortex areas. So this is an image from their paper where they're kind of explaining like how this perturbation technique works. But from what I can tell, they have this function that's modifying brain states. So it looks like the input is the time series, and the output is some kind of perturbed state. So I think from what I can tell, they want to judge their model's response using, it looks like the L2 loss between the input the perturbed state and the target state. So in terms of how their model generalizes, they evaluated their model on the UK Biobank dataset and the HCP dataset. So they achieved strong generalization with an average R-squared score of 0.4 on the UK Biobank test set, influenced by the training data size and masking ratio. And their claim is that it generalized well to the HCP dataset with an R-squared score of 0.3. So I'm assuming that this R-squared score is a similarity score or some kind of a correlation coefficient. And they also kind of detailed their results on the prediction of these clinical variables task. So what they did was they evaluated their model's clinical prediction abilities by fine-tuning on this metadata that was collected at the time the fMRI was collected. And this came from the UK Biobank dataset. So again, they appended this MLP head to the pre-trained encoder for in order to predict age, neuroticism, PTSD, and anxiety disorder. And they achieved lower mean squared error compared to SVMs on raw fMRI data and BrainLM embeddings. So this, they're claiming, is showing how their model can achieve a robust representation, learning, and transferability.
Kind of a bad.
Oh,
But
what was the question?
I think it's kind of a poor baseline. There are other models that do this stuff, but whatever.
Yeah, I kind of agree with that as well. But I guess this is their way to kind of state that their model has, better accuracy in an easy way. But yes, so they also visualized the self-attention weights that were learned. And they were just kind of trying to see, I guess, what kind of representations were learned during training. And they also looked at the task-based fMRI, and they were seeing heightened attention in the visual cortex compared to resting states. And when it came to looking at mild versus severe depression, they saw that the attention patterns after visualizing their attention weights were differing. And they were finding these functional variations that were relevant to other clinical conditions and literature. So in terms of reconstructing the time series data, obviously they wanted to show their results after reconstructing on the held out data. So this is data that their model had not seen, and then their model was to reconstruct this data. So in the figures that they're showing here on the left-hand side, they're claiming that their model accurately reconstructs data from both its training cohort and its external cohort, demonstrating strong generalization of their model to unseen data. So they're saying their model's ability to match predictions with ground truth showcases its robust performance across different data sets and subjects. They also did a more analysis of their results of this perturbation analysis. So again, they use these pre-trained representations. So they essentially, from what I can tell, did their training of the encoder, and then they froze the encoder weights and mapped all the data set to this lower dimensional space. And then they did this perturbation analysis, which is basically where once they have the data set mapped to this lower dimensional space, they kind of like tweaked it slightly and then provided this as input to the decoder. And so they used this optimized perturbation technique, and they looked at the difference between resting state and task-based fMRI. And they found that this revealed key regional differences, specifically in the visual cortex. So I think there's going to be maybe some images on the next slide of this result. But basically they're saying the fact that they found this with their perturbation analysis shows that their model is able to uncover these intrinsic knowledge of functional connections across different contexts and age groups. So they're saying they were able to do this without additional tuning using their perturbation function. So this is some of the results. So their perturbation of resting states to match task-based recording revealed functional changes. So we can see in figure 7 that it looks like their silico perturbation from resting state to task-based fMRI is depicted. So it looks like the average magnitude of optimized perturbations to make resting state CLS tokens match target CLS tokens is depicted in this image. So they found that the region with the largest predicted perturbation is the visual cortex, which is in line with their expected findings. And specifically, they were expecting to see the largest changes in the visual cortex with comparing the functional changes between resting state and task-based recordings. So they're saying that this, they did this kind of like perturbation technique to demonstrate their model's ability to simulate responses in a biologically meaningful manner. So in terms of their functional network prediction, I think this is one of their downstream tasks that they had. They evaluated their model's ability to segment fMRI parcels into 7 intrinsic functional brain networks. So they compared the parcel classification methods with the KNN on raw data. They also compared it with a variational autoencoder, as well as GCN embeddings. And so they looked at these compared with their self-attention weights. So from what it looks like, their model is achieving a high accuracy. It looks like the second best accuracy was a variational autoencoder. And last looks like the graph convolutional network. So their model's attention-based approach outperformed other methods, achieving 58.8% accuracy, demonstrating unsupervised learning of brain networks solely from pre-training. So, in summary, they're claiming the first foundation model for fMRI analysis. It utilizes this self-supervised pre-training, and it operates on, it was trained on extensive brain activity data. And they found that their model demonstrated high accuracy at reconstructing masked brain activity sequences, as well as it generalized well to unseen distributions. Their model also enables biomarker discovery, as well as computational modeling of brain function. And they kind of did these meta-analyses, I guess you could say, for this just, I guess, kind of like another test to validate their model, which was this perturbation analysis, which gave them interpretability. Again, and they were able to kind of change the input or kind of modify the brain activity without obviously live brain intervention. So yeah, guys, I think overall this was kind of an interesting paper. I think this model is pretty cool, especially with the hype around like large language models. And I think it would be cool to, see this used in our lab potentially. But yeah, guys, does anybody have any questions or comments?
Yeah, I think this was inevitable right after there's been the EEG foundational models and a couple other neuro LMs that came out. This was just waiting to happen. I think it'd be interesting to compare an approach with a different parcellation technique. That'd be one easy thing to contrast with. I mean, you mentioned the mixed parcellations that they use. Seeding might be, yield better results maybe, but I mean, you're just kind of tweaking things at this point. But this was a low hanging fruit in my opinion, but they were the first to kind of snatch it and did some kind of interesting things with it, it seems.
Yeah. Yep, okay.
Perturbation,
Yeah, go ahead, Brad.
how it works, but whether that's
Yeah, I was honestly like really confused about that as well. I think there's some kind of a function that learns. Hold on. My slides are not showing. Yeah, I'm a little bit confused about that as well, but I think I'd need to look into that a little more.
So one thing I will say is this is not some of the work on perturbation analysis, similar. There have been attempts to do something similar, but with an explicitly model-based, with an explicit dynamical model system
versus a learned model like they did.
versus an autoencoder. So my own previous lab, the Gustavo Deco lab in Spain, came out with a few model-based approaches to do the same thing. I think about 3 years ago. It's still something that's worked well. He's kind of changed tack since then, but it's something that he's been interested in for a very long time. I'm sure he's still working on it, I don't doubt. And he was actually able to demonstrate some pretty. So he was able to demonstrate some pretty important results. I was able to show, for example, which types of stimulation could change a person's state of consciousness, specifically from the sleep state to the awake state. That might be something to look into as well.
I think looking at these results again, I think it's rather underwhelming. Some of the stuff that they do with it, like I already mentioned comparing with the SVMs and this other task, this other thing that they do, guessing the brain networks. I mean, we could do that with ICA for free, with Neuromark ICA more consistently. It's just like they kind of did it. All right. I don't know. The upshot here, Like what can you do that's really, really novel? I'm not really along for the hype, but I don't know.
Yeah, I think overall it was just kind of an interesting experiment. And I think something like this would have been coming obviously with like large language models and stuff. Um so yeah, I think it's a starting point. So hopefully someone else can build on this.
I'm looking at the reviewers on their open review as well. None of these people are neuroimaging people. You can tell it's like, yeah. One of them says that the authors collected UK Biobank, which is funny. Anyway. Yeah, no, yeah, they did it. There it is.
Okay, guys, any other comments or questions?
Thanks, Joanne.
All right, guys. Well, thank you so much. And I guess, Ksenia, you can share this recording to the cloud.